Good morning, everyone. So I'm going to present this work which I'm doing with my collaborators at ICTS. And so we are going to present you a Bayesian method for selection of the various population synthesis models of the compact binary coalescence. So the detection of the gravitational wave by LIGO opens up a new window to observe the universe, and now it starts an era of gravitational wave astronomy from the gravitational wave detection. And in the next decade, we will have a network of detectors when the LIGO India and Kagra will join, along with the advanced LIGO and Virgo. And we expect many more detections of compact binary coalescences as we had last year. So the main source of the gravitational wave for the LIGO detectors is the merger of two compact objects, and here we show a waveform of from a binary black hole merger with the masses of 20 and 10 solar mass. So this is the in spiral part, and then this amplitude increases and it merges at this point, and then there is a ring down phase which we cannot see here. For this you have to zoom in. Okay, so there are various channels of the formation of these binary black holes or the compact object, but the astrophysical processes and the physical processes which governs this evolution, this is poorly understood. There are various population synthesis code which simulates these processes, and they provide the estimates of rates of the double neutron star mergers and the neutron star black hole and binary black hole mergers. And these rates differ for different models, and usually these models are parameterized by various unknown parameters like the metallicity and the binding energy of the envelope and maximum mass of the neutron star, the kick velocity, and etc. etc. And in the upcoming years we expect many detections. Then we can, so we aim to constrain these population synthesis models from the detections of the binary black holes in upcoming years. So this Dominic et al., they have provided this publicly available population synthesis models, and you can look at these models in this website, the syntheticuniverse.org, and we consider the binary black hole mass distribution and for our analysis. Okay. So this is the classification of the population synthesis models which is provided by this Dominic et al. And these models are parameterized by various parameters. So there is a standard model for which this lambda parameter, which is related to the binding energy of the common envelope phase, which is it is given by this is called the Nanjing lambda, which is basically a value which is given by the group at the Nanjing University, and they take this maximum neutron star mass to be 2.5, and then they take this Maxwellian sigma on this distribution of the Natal kicks, and then there are various other parameters. So we can group these models into the various subgroups. Like we can take standard model along with all other models in which the lambda varies, which is lambda is a parameter related to the binding energy of the common envelope phase. And similarly, they have in the two models, they have taken the maximum neutron star mass to be different. In one case it's 2, in one case it's 3, in the standard model it's 2.5. Similarly, then they have different sigma for the Maxwellian distribution on the Natal kicks for the black hole. Similarly, they have this delayed supernova engine and all that. So each of this, so they have total of 16 models, and each model is has two submodels, submodel A and submodel B, which is basically related to the. In one case, they ignore the boundary issue between the core and the envelope, and in another case, they take the conservative estimate. And along with each submodel is divided into two other submodels, which is sub-submodels, which is one with the solar metallicity, another with the subsolar metallicity. So we have total of 64 models. And the idea is that, okay, so this is the component mass distribution of two of the models, which is the standard model and with the submodel B, with the solar and subsolar metallicity. So if you see that each model predicts the different component mass distribution and also different rate. So if we have, say, tens or hundreds of observations of the gravitational wave event, then we can see whether so we can then constrain this parameter space of these models. So we use this Bayesian inference method to rank these models. Here is this, so the posterior for, so if we assume a model and we have some data D, then the probability of this model parameter theta, assuming this value is this given by this posterior distribution, and it is related to with the likelihood function and the prior on this model. And this quantity is in the denominator is the evidence. So we can calculate this evidence for different pop-synth models, and then we can rank them according to the value of this evidence. So one thing to we need to look for is how to account for the selection bias. So the observed mass distribution does not represent the actual true mass distribution, because the higher mass events are more likely to be detected than the lower mass events. So we have to account for this selection bias. One of the we can avoid the selection bias by basically accounting for non-detection and perform the full Bayesian analysis by which was described by this in a paper by Chris Messenger and John Veach. And also we can calculate the selection function using the large number of injections in the data analysis pipeline, and then we can see so in each mass bin what's the fraction of masses which are recovered, and using that we can calculate this selection function. So I present these challenges so this is a currently ongoing work. We are looking for how to account for the selection bias in an efficient way, and also we have to account for the uncertainties due to the poorly understood astrophysics, whether we are accounting all these uncertainties or not. So keeping these challenges in mind, we move forward. So we simulate the population of the binary black holes from mass distribution predicted by this various population synthesis model, and then we distribute them uniformly in the co-moving volume up to a redshift of 0.5, and then we calculate the evidence for each model depending upon the number of detection in that model we have. And we expect that for the large number of detection, we recover the fiducial model, and then we can rank the other models depending on the evidence calculation. Okay, so to estimate the parameters for each of the simulated event, we use this LALInference code, and we use this nested sampling implementation in it. And then this is an example of one of the posterior for one simulated event, where we estimate the masses of the two black holes from this. Okay, so this is our analysis for we took the 7 model, one subgroup of model in which we vary the lambda, lambda is a parameter which is related to the binding energy of the common envelope, and we for each row represents the universe. I mean, this is the simulated universe, and in each universe we calculate the evidence for each other model. So this is with the 15 simulated observation with the network SNR threshold of 15. So you can see that in each of the case we were able to recover the fiducial universe, and then we can rank all other models in that particular universe. Similarly, this is for the other subgroup of pop-synth model, which is parameterized by the variation in the natal kick that a black hole receives. And here also we were, with the 24 simulated observation, we were able to recover the fiducial model, and then we can rank all other models in that particular universe based on the evidence calculation. So to summarize, as we enter into the era of this gravitational wave astronomy, the future detections from this gravitational waves from compact binary, using these observations we can distinguish between various population synthesis models, and with large number of detections we can even rule out various models. And yeah, with this I